This one for all my peeps that pass. God bless they rest. And check it out. Now I'm pound cause it's mad real.
Yo, it's time for Carnegie Mellon University's Future Data Systems Seminar Series. This seminar is made possible by Google.
Alright guys, let's get started. We're excited today to have Chen. He was the co-founder of Mooncake, which he's happy to say got acquired last month, right, by Databricks. Congrats. And he's here to talk about the Mooncake extension they were building out in Postgres to interoperate with Iceberg that's now being put into the Databricks infrastructure. So as always, if you have questions for Cheng while he's giving a talk, feel free to unmute yourself and fire away at any time. That way he's not talking to himself for an hour by himself on Zoom. And Cheng, thank you so much for being here. The floor is yours. Again, congrats on the acquisition. I'm glad you could still make it.
Yeah, thank you, Andy. Hi everyone. So I'm Chen. It's an honor to be here today and share what we are building at Mooncake Labs. So a few months ago, my co-founder wrote a blog post titled HTAP is dead. And that sparked a debate in data community about the future of hybrid transactional and analytical processing. So the dream of a single monolithic HTAP engine that seamlessly handles both transactional and analytical workloads hasn't played out as many of us hoped. But the need for fast analytics on fresh transactional data hasn't gone, if it's not stronger than ever now. So today, I will walk through how to build a composable HTAP stack, one that bridges together your existing OLTP system and your existing OLAP engines, designed for the cloud era and then powered by open data formats. Yeah, as Andy said, if you have any questions at any point, just feel free to interrupt me and just drop them in the chat. So a bit about myself. So I joined SingleStore right after school and spent many years on the core execution team there, building a monolithic HTAP engine. And last year, I left SingleStore with 2 colleagues to start a company called Mooncake Labs. So yeah, don't tell me why it's called Mooncake. There's a story, but just think of that we are selling Mooncake. So the goal of the company is that we want to do this with a new approach. We want to build a HTAP in a composable way. Yeah, I will explain very soon what that means. So just last month, after a 13-month journey, Mooncake was acquired by Databricks, and we are starting a new chapter with the Lakebase team at Databricks. So Lakebase is a Databricks Postgres offering. It's serverless and deeply integrated with the Lakehouse. So let's look back to the history. In the good old days, so one relational database can do everything. Transactions during the day and reports after the hour. However, as the businesses had more data and asked tougher questions, the database this kind of one single database has begun to show its limit. OLTP requires microsecond inserts and point lookups, while OLAP demands full table scans and large-scale aggregations. So this creates a constant contention and poor systems in different directions. So on the analytics side, column storage, and vectorized execution emerged to accelerate the scans and aggregation that's common for analytics workload. This changes both how data is stored and how queries are executed. And the cloud fully changed the game. Separating compute from storage enabled fully serverless elastic analytics. The Lakehouse then unified the storage layer. Now data lives on an open format on shared object store, and multiple engines like Spark, Channel, etc. can process the same data for ETL, BI, and AI, all in a single shared data layer. However, on the transactional side, early NoSQL systems tries to address the scalability limits of relational database, but it gave up transactions and consistency. And new SQL systems try to put them back while scaling horizontally. But despite a few successes, it never became mainstream as analytics rapidly moving to the cloud data warehouse and the lakehouse. So where this leaves us is a world like with 2 distinct systems. So one is optimized for transactions and the other is optimized for analytics. And the users are forced to manually duct tape them together with complex and fragile data pipelines that takes hours to sync and sometimes transform data into something that's hard to read. So that spawns up a natural question. Can we do better? So the original vision of HTAP, what I call here monolithic HTAP, was to build a single engine that's capable of serving both OLTP systems that can serving both OLTP workloads and OLAP workloads. And we actually spent the last decade at Single Store working towards that vision. So at Single Store, there is only one copy of the data and one engine that powers both transactional and analytical queries. Hot data stays in the in-memory load store, while cold data lives in the on-disk column store. The column store was engineered to be operational. We added secondary indexes and a better seekability to this column store to support fast scans, seeks, filters, and aggregations. And the system is fully distributed. It can scale from a single node to thousands of nodes. It also supports like semi-structured JSON data and can integrate search and full-text search, vector search seamlessly into SQL. So Single Store is a strong and versatile system, but it never achieves the traction we hoped for. And ironically, if you ask many former Single Store engineers today, they will just tell you, don't build a HTAP system and don't build distributed SQL. So this is a better lesson I learned from Single Store. The better lesson is that true HTAP is extremely niche. So the really hardcore HTAP system, the really hardcore HTAP use cases that really requires a monolithic HTAP engine that both workloads runs in the single engine, like Single Store, is you need to run analytics inside transaction. So for example, one typical example of this is fraud detection. You want to perform analytics in real time within the transaction, and you want to use the result of that analytics query to decide whether to approve that transaction or not. But most of the workloads that involve both OLTP and OLAP are not like that. People are more interested about running fast analytics on fresh data, and the goal is to make smarter and faster decisions. And for those, you don't really need a monolithic HTAP engine. So that's the market side. So from the engineering standpoint, building a monolithic engine also puts you in a very tough spot. You are competing with both the best OLTP engines and also the best OLAP engines, you are trying to replace both of them and replacing users' existing OLTP and OLAP systems that usually have tons of workload already relying on that. And these challenges even compounded because OLTP and OLAP are often owned by different teams within the same organization. So moreover, creating a single engine also forces trade-offs, compromising both workloads, and you are just compromising for a niche use cases that most users never will use. So it's just they are hoping that maybe one day they will be using it, but most of the time they will never use it. And finally, OLTP and OLAP schemas are usually different. So using the same copy of data like Single Store does, in many cases doesn't make sense in practice. So when we look at the real winners in the market, so Postgres is winning on the OLTP market, and cloud data warehouses and lakehouse are the dominating usage for the data team. So Postgres remains the most loved OLTP database, thanks to its reliability and openness and a rich ecosystem for extensions. There are thousands of extensions. You can pretty much find anything you want just with a sea of extensions. For all the no-OLTP workloads, Lakehouse built on top of open formats like Iceberg and Delta, they are emerging as a unifying data layer, enabling both analytics and AI workloads to run across multiple execution engines on the same underlying data. So what does HTAP really mean if the OLTP is dominated by Postgres and the data is dominated by the Lakehouse? So my understanding is that it's not really about building one magic engine that try to replace people's people loved Postgres and Lakehouse. It's about giving that is already a fact. Let's build something that tries to bridge existing OLTP and OLAP systems so they can work seamlessly together. And the goal is to simplify the usual data stack. So in that sense, I think in the more realistic sense, HTAP is not really a new database catalog. It's more of a feature of your data stack that if you want to turn it on, it can enable real-time analytics on your transactional data. So this is what we proposed as a composable HTAP stack at Mooncake. So users can continue using their favorite OLTP and OLAP systems. It can be Postgres, but it can even be like MySQL for transactions. And for the analytics side, you can use any execution engines on the open data format provided by Lakehouse. So what Mooncake adds to this is a real-time layer on top of Lakehouse and enables sub-second ingestion from OLTP to OLAP. And we also allow like directly read from OLTP for fresh analytics. So this is a feature you can turn on demand for your data stack. So this makes our decision to join Databricks simple. So Databricks is already a pioneer in Lakehouse, offering the best-in-class Spark for massive scale ETL and analytics. And their recent acquisition of Neo adds serverless Postgres offerings called Lakebase, complementing the Lakehouse story. And they also have Unity Catalog that provides a unified governance across both the transactional and analytical data. And the Mooncake team joins Databricks to help build a stronger bridge between the Lakebase and the Lakehouse, continuing our composable HTAP vision, but at a much larger scale. So in the following, I will do a tech deep dive into Mooncake. There are two components we built. First, I will cover Moonlink. This is the real-time layer we built on top of Iceberg that also enables a sub-second ingestion into Iceberg. I will talk about how we build this incrementally, one step at a time. Then the next part, I will talk about PG Mooncake, which allows directly fast analytics in Postgres and integrates Moonlink. And when combined with Moonlink, it provides a complete HTAP solution directly inside your loved Postgres. So this forms the composable HTAP framework. And while the talk here are focusing on Postgres and Iceberg, but the same idea applies to other OLTP systems and OLAP systems. So let's look at the Moonlink first. So when building a real-time ingestion into Iceberg, the challenge actually isn't in the ETL itself. The real difficulty comes from the fact that the destination analytics system simply isn't real-time enough to keep up with the source, the OLTP transactions. So our goal here is to support both streaming and batch writes, and for both insert, update, and delete. And we also want to make the destination table always optimized for read. And the latency from the data is generated from the source, from the OLTP Postgres side, to when it's applied and readable on the destination's analytics side needs to be extremely low, on the order of sub-seconds to be truly considered real-time. So there are several difficulties for each of them. So for streaming writes, the existing CDC tools often write to the destination for every single source write. This creates thousands of tiny Parquet files, explodes the metadata, and makes the reading very, very expensive. And this also requires frequent compaction, which is also costly and disruptive. And for update and delete, this makes the problem even worse. Many of the CDC tools, they directly just write equality deletes. So what is equality deletes? They just write like which key are deleted, and they're not actually writing the position. So they require the readers to handle them at read time to join these deletes and the actual data at query time. So this further slows the reads down. So batch writes also have their own issues. So most systems will wait until, let's say you do a large, big insert into the Postgres. Most of the CDC tools will wait until this large batch write transaction has been committed, and only then they start to stream the changes and applying the changes. So this introduces unbounded latency after the source has been changed, and the latency can be proportional to the size of your writes. So Moonlink is designed to solve all these challenges by adding a real-time layer on top of Iceberg. So yeah, Moonlink is built on top of like previous engines inspired by many previous work. So during the short time of Mooncake Labs, we actually re-architecture our design. So our previous version, PG Mooncake v0.1, it works very similar to other CDC tool, most of the CDC tools. It basically handles the write. It basically only allows like batch writes, and we wrap everything inside Postgres. So every time the Postgres does a write, batch write, and we also do a write, make a new commit inside the Postgres. So it can only handle batch writes. So this kind of only works well for casual data warehouse use cases. The only good thing it adds is you can do everything inside Postgres, so it's easy to use. And when we try to sell this, some users try to use it for streaming rights because they are just expecting everything just Postgres, and it didn't go very well. And this actually led to us why we rethink the architecture and try to include this HTAP experience into it. So we also draw inspiration from TiDB. So TiDB is another HTAP system. So unlike single store, TiDB actually maintains two copies of data, one copy for transaction and another copy for analytics. And they have a real-time ingestion from the load store to the column store to keep them in sync. But TiDB also has their own limitations. It forces your column store clustering key to match the load store primary key, which is very restrictive for column store. And ultimately, it's still a monolithic HTAP engine. So they are claiming that you need to use TiKV to replace your OLTP system, and you need to use TiFlash, which is a ClickHouse fork, to replace your OLAP. So another relevant project is Flask. So Flask forces users to adopt PyMo. So this is a different lakehouse format. It's one that's more real-time. So what Moonlink does in contrast is it makes no assumption about the underlying lakehouse it's being used, and it's composable with like different OLTP and OLAP systems you want. Yeah, before we dive into the internal workings of Moonlink, let's first look at what is the input and output we are talking about here. So the input comes from Postgres logical replication. So we can subscribe to the changes of Postgres, and we can subscribe to like a specific set of tables or the entire database. So when transactions are run in Postgres, the changes are first written to the wall, and the changes are written to the wall in the order they occur. And the changes from different transactions, they can interleave with each other within the wall. And for logical replication, Postgres uses wall sender process. They are going to read changes from the wall and replace them into a reorder buffer. This buffer will group the changes by transaction and order them by transaction commit LSM. So what does that mean? That as a result, the receiver, what we see is just one complete transaction at a time in the order when the transaction commits. However, this only works for small transactions. For large transactions, we definitely don't want to wait until the entire transaction already commits before starting streaming the changes and applying the changes to destination. They will introduce unbounded latency. So Postgres 16 enhanced their support for logical replication. It added support for streaming large transactions. So when the reorder buffer are filled up, so Postgres is going to select the current in progress transaction that's largest and send these changes in a streaming block like this. So these large transactions can later be committed or aborted. And And at any given time, there may be several large transactions interleaving with each other, but along with the usual stream of small transactions. So one important thing to note here is that the streaming is optional, so it's not necessarily turned on. And even when it's turned on, there's no guarantee that you can always see the uncommitted changes within the transaction. So this is the limitation of Postgres logical replication. That basically means that if you really want to build a true HTAP that actually you can run analytics within transaction, you can do that. So for Moonlink, that's fine because our goal is not to run analytics within transaction. We just want to run analytics on fresh transactional data. So let's also look at the destination. So this is a very extremely simplified version of Lakehouse open format that we are writing to. So at its core, it's just data files, mostly Parquet files, but they also support some other data formats. And the metadata and also adds metadata to these data files that helps you construct the count snapshot of the table. So Iceberg and Delta does differently for the metadata. Iceberg metadata directly lists the count snapshot of the table. So each snapshot contains a list of data files that makes up the count version. And the Delta does it differently. Delta metadata tracks the changes, like at each time, like which files are added and which files are deleted. This is a very simplified version, like there are more details into it. But in the end, it's just the same data file plus some flavors of metadata. And for us, it doesn't make too much differences. So both formats also support deletions in different ways. The simplest way is the equality deletes, which I just told you the problem with that. So with the equality deletes, the records, we only record the deleted keys and rely on the reader to duplicate that every time. Iceberg v2 improves that by introducing positional deletes, storing a separate Parquet file that lists the positions of loads to delete. And Iceberg v3 goes further with deletion vector files. So using a bitmap to identify which loads in a Parquet file shall be considered delete. And for us, for Moonlink, we write deletion vector since it's optimized for read. Cool. Now let's see how Mooncake works. And I'm trying to do it in a step-by-step way. So let's start from the simplest case. The simpler case is we want to support streaming writes with just insert. It's append only. So the challenge here is that we can't write to Iceberg too frequently. We need to buffer the latest writes in a low log and write to the Iceberg only occasionally. But at the same time, we need to provide a consistent view so that the readers can read. We need to read at much frequently interval compared to the frequency we write to the Iceberg, to Delta. So in order to do that, we have to do some kind of union read to serve the data from both the buffer and the Iceberg. So more specifically, the way we are doing that is we decouple a Mooncake snapshot from the Iceberg snapshot. So what Mooncake snapshot does is it's kind of a lightweight snapshot, and it can serve reads for union read. And we take a Mooncake snapshot every 500 milliseconds, while the Iceberg snapshots are only created like every 5 minutes. Or when there are enough changes or has already accumulated, we also take an Iceberg snapshot. And the Iceberg snapshot is taken based on the most recent Mooncake snapshot. So here is the example. So let's suppose we already have an Iceberg snapshot with like 4 rows. Now we do a new insert. And when this insert comes in, we just append it into the in-memory arrow buffer. And the combination of this in-memory arrow buffer plus these Parquet files will allows us to union read the latest data, the count snapshot. As new rows are getting appended, we just keep appending them to this arrow buffer and create Moonlink and create Mooncake snapshots every 500 milliseconds. And when it's time to create an Iceberg snapshot, we just flush this arrow buffer into a Parquet file and forming a new Iceberg snapshot from the latest Mooncake snapshot. Yeah, so this is how it works for streaming writes and just append only.
Just to be clear, the arrow buffers that are in memory, that's sitting inside the Postgres process because that's where the Mooncake extension is, or is this outside of it?
So Moonlink is by itself a raster binary. It can be run inside. So in PG Mooncake, we have like two different ways to deploy Moonlink. One is just we deploy that as a background worker. So it's inside Postgres. Another way is we just deploy it as a standalone service. So the PG Mooncake can just attach to it.
Got it. All right, so then I understand you're transitioning from a standalone company to integrating this with Databricks, but what is the plan? How would you integrate this with like Neon?
Yeah, I think so. This separation, these two deployments even exist before we joining Databricks.
Okay.
So Moonlink is just a single raster library, and anyone can just include it inside their binary. And in PG Mooncake, we just one way of deploy it. We just deploy as like a background worker in Postgres.
Yeah, I understand that. I'm trying to say, like, what can you share what the plan is going forward since PG Mooncake is now, part of Databricks? Like, how's operationally Databricks going to deploy this? Like within Postgres itself or as a standalone service?
Yeah, right now, since we just joined Databricks, so they actually already have some kind of forward ETL, which does something very similar to the current Moonlink. And
Okay.
right now, it's not really we try to deploy Moonlink inside Databricks. It's more of like we are trying to add more capability, add the tags we developed at Moonlink and try to enhance that thing.
Got it. Awesome. Thanks.
Yeah, so this is streaming rights and append only. So now let's add support for update delete into the streaming rights. So let's still first look at the source. Postgres uses replica identity to identify a load when updating to replicating updates and deletes. By default, the replica identity is just a primary key, but can also be set to a unique key or even like the entire load if suitable, there's no suitable exists. So the goal of that is just to identify the load so you know which load to delete, update. So for replication, delete will send the old replica identity and to indicate which loads to remove. And the update will send both the old replica identity and also the new tuple. There's also an important note about toast columns. Toast column stores like large values that don't fit in line in the heap page. When replicating update, when the toast column is unchanged, Postgres will by default optimize that and only indicate that it's unchanged without actually sending the actual toast value like this. So currently, we simply just instruct Postgres to send the entire load by running auto table replica identity full, but this can be optimized in the future. So the difficulty in update delete is we need to translate this replica identity, this equality deletes in Postgres into a positional deletes that's better suited for efficient reads. To do this, we need to build a hash index. This hash index is mapping from the hash of the replica identity, not directly from the replica identity, to the position of the load, which is just a pair of file ID and load ID. So we need to build this hash index for both the in-memory arrow part and also the on-disk Parquet part. For the in-memory arrow part, we just use the in-memory hash table to index it. For the Parquet part, we use the disk optimized hash table to index it. And the Parquet index are stored in the Iceberg pathing files. So it links this index to the correct Iceberg snapshot. So if anyone else also wants to read the hash index, they can also use it. So because the key is just the hash of the replica identity, so the hash table is really small, and we can catch the entire thing on local disk. So an important optimization here also answers why we can just use the hash of the replica identity, is that because we are simply mirroring Postgres. So if Postgres says that a load can be deleted, that load must exist. This means that if anytime we search for the hash of the replica identity and find only one load, this load must be the one we are looking for. So unless there is a hash correlation, it's just one hash table lookup to find the load. We don't need to actually compare the replica identity or need to read the data files. So the on-disk index is structured as index LSM. So if we have had a single hash table covering the entire table, So think of the other way. If we have a single hash table covering the entire table, then every table update will require updating the index. On the other hand, if we had a one hash table per data file, then each lookup would require scanning all the indexes, which is very inefficient. So with the index LSM, each index is built for a subset of data files and only needs to be updated when those files changes. So this provides a good balance between write and read performance. So this approach inspired by single stores index, which uses the same index LSM structure for different types of singular index, including hash index, full text index, and vector index. And the hash table is disk optimized. So each individual hash table, each hash lookup is just two seeks. So now let's see how update delete works. So with these building blocks in place, the key idea here is to just add a delete log. So when update deletes are replicated from Postgres, we first append the replica identity, the equity deletes, to the delete log. And this happens in the foreground and it's very fast. In the background, the Mooncake snapshot will translate these equity deletes into positional deletes using the hash table. Then the Iceberg snapshot updates the deletion vector with the positional deletes from the Mooncake snapshot. So for example, imagine we have an Iceberg table with 4 rows. First, we add 2 new rows, which are buffered in the arrow. Next, we delete 1 row from the buffer. This delete is initially recorded as an equality delete in the delete log. And then the next Mooncake snapshot will translate into a position delete and pointing to the row in the buffer. Then if we update the row in a Parquet file, the old row is also marked as deleted. We do the translation pointing to this row. And at the same time, we also add the new row to the data log. And in the following Iceberg snapshot, this positional delete and also the data file will be flushed into the deletion vector and the Parquet file. So the next thing we do, we are going to add support for large transactions. So to handle them, we need to enable logical replication protocol v2 so that Postgres can stream in-progress transactions. We also need to apply these uncommitted changes on the fly ourselves. To do this, the idea is basically we maintain a separate load log and a delete log for each large transactions. And we also allow Parquet files to be flushed in the middle of the transaction rather than waiting for the entire transaction to commit. Otherwise, a large transaction will just overflow the memory. So one important detail here is that when we translate the equality deletes into position deletes during a Mooncake snapshot, this translation operation needs to be global. So for example, under read committed, imagine you have a large transaction that's running and also a small transaction commits in the meantime. This large transaction should now be able to see these newly committed loads from this committed small transaction. So this deletion transaction must take both this large transaction and small transaction into account. It needs to be global. So oftentimes we are creating a column store mirror of a Postgres table that already contains a significant amount of data. So we need to perform an initial table copy in a way that's consistent and parallel. So the workflow is as follows. So first we create a logical replication slot, and also we export the snapshot from it. Then we start n parallel workers, each responsible for copying a slice of this table, and they are sharded by the Postgres CTID. Each of the worker will, so these workers will read from the expected snapshot exported from on the first part. So they will all see a consistent view of the table. And once the parallel copy has been finished, we begin the replication from the slot and applying incremental changes. So the entire table is a consistent memory. So we also need to be able to recover from crash. So one naive approach that we tried at the beginning is to rely entirely on Postgres WAR. So basically, we will only acknowledge back to the Postgres LSN that has been flashed to Iceberg. That way, the logical replication slot never advances past what the Iceberg has persisted. So after a crash, we can just ask Postgres to resend all the changes that we haven't seen and just reapply them. But this actually creates an issue. we end up having the logical replication far lagged behind the count LSN in Postgres. And this can block the Postgres from shutting down. To address this, we actually need to add a Mooncake wall, a write a hello log ourselves. And we acknowledge the LSN back to Postgres as soon as it's written to the Mooncake wall, not only after like it's flashing to the Iceberg. So this lets the Postgres replication slot to move forward without being held back. So one nonce here is that Mooncake wall is written after the Postgres reorder buffer. So the record order isn't the same in Postgres wall. And during recovery, we need to actually carefully reconcile these three things: the latest Mooncake snapshot, and sorry, the latest Iceberg snapshot, the Mooncake writer log, the Postgres wall, and make sure everything stays consistent. So another thing is that we also need to run background mergers to periodically compact small data files and indexed files into larger ones. So compaction is heavy. But the issue here is that compaction is a heavy long-running transaction, and it should not block concurrent writes. So for example, suppose the Iceberg snapshot currently consists like 2 Parquet files here. And now we start a module process to start compile them into one. So while this is running, there are concurrent insert and updates coming in, and new Mooncake snapshots have been taken for this. And when this compaction finishes, we can just commit this compaction because it will conflict with the delete records in the delete log, because the delete are still points to the previous low positions. To handle this, so when we compact these 2 Parquet files, we also build a remap table that maps the old lows to their new position. And before we committing this compaction, we quickly walk through all the deletes in the delete log and remap these deletes to the new low location. And this remapping process is fast. So now after this remapping, this compaction can commit. We can even further optimize this by breaking this large compaction transaction into smaller incremental ones. We haven't done that currently. It's also important to define a clustering key on the column store, whether that's a hash key or sort key or something more smarter like a liquid clustering. This will allow us to skip files more efficiently at read time. We were just in the middle of building this when we get acquired. And now when we join Databricks, we can just take advantage of the clustering capabilities they already have. So now let's put it all together. So Moonlink adds a real-time layer on top of Iceberg through the buffering and the indexing. So we buffer both the lows in the allo buffer and also the deletes in the positional deletes. And we also build index to make the translation fast. And it supports both streaming and batch writes with fast update and delete support. The engines can just directly read the historic data directly from Iceberg, but if they want to read the latest changes, they can do a union read directly getting it from Moonlink with sub-second latency. So in the foreground, we only consume the Postgres CDC, and we only append the new loads to the allo buffer and record the equity deletes into the delete log. So this is a critical path and extremely fast. All the heavy work happens in the background. The Mooncake snapshot, the Iceberg snapshot, the compaction, and none of them will block the replication in the foreground.
So like you're writing out Parquet files that can contain data from uncommitted transactions, right?
We only do that for large transaction.
Sure, I understand that. Like, but it means like you're still doing it. Like someone does a large transaction, you have to do it. And then if that transaction then fails, I guess the deletion vector is saying ignore that thing that's been removed, or where do you keep track of like, I wrote a Parquet file that has uncommitted changes. The transaction then fails. How do I then rectify that I shouldn't read those changes?
When Parquet files are flushed for large transactions, these Parquet files are not committed, and we are not actually writing it to any of the Mooncake snapshot or Iceberg snapshot. It's not valid to write it.
Got it. Okay. Yeah. Makes sense. Okay.
We just track them. Yeah. So one last part.
So does that mean that like uh if for the large transaction, if it does commit, do you then push that Parquet file into Iceberg?
Yes,
Got it.
actually,
Okay.
the Parquet file is already uploaded to S3. So the only thing we do is just to basically move the name, the path of the Parquet file into the metadata to track it.
Yeah, got it. Okay, thanks.
So one last thing about that is schema evolution. So when the schema of a Postgres table changes, how can we capture these changes and apply them to the destination Iceberg table? So in fact, capturing schema changes in Postgres is not trivial. Postgres sends a relation message in logical replication that includes the column names and the column types, but that's not enough to fully reconstruct the schema changes. So this limitation does not just apply to us, but it also affects Postgres building logical replication. When the source table schema changes, the replica can draft from the primary. So one workaround we can do is to use event triggers to capture the schema changes on the tables we are interested in. And we serialize these schema changes, use this special PG logical emit message to record that on the wall. And then on the subscriber side, we can deserialize these changes and apply the schema changes to the Iceberg. Yeah, this we only have partial support for it. Yeah, okay. So this is about Moonlink, a real-time layer on top of Postgres, which allows us to do fast sub-second ingestion from Postgres to Iceberg. Now let's talk about PG Mooncake. So PG Mooncake enables fast analytics directly in Postgres. And when combined with Moonlink, it delivers a composable HTAP experience. So the usual interface is like, so let's suppose the user already have like a Postgres table, regular Postgres table. Now they can run call mooncake.create table and specifying the column store table. And this is the load store table saying that I want to create a mooncake table as the middle of the Postgres table. The full syntax table also allows you to specify the where this Postgres table resides in. It can be a remote one. You can replicate mirroring from a remote Postgres like RDS. You can also configure table options such as where to store the Iceberg table and how it should be clustered. And once this Iceberg mirror has been created, it just behaves like regular Postgres table. You can even join it with other Postgres heap tables. The only thing is that this is read-only, that you should do the write into the Postgres table, but do the read from this Iceberg table. You can also do the read from the Postgres table directly for transactional workload. It might be possible to build some kind of syntax trigger that you also allow writes into this column store table, where it federates back to insert into the remote or local Postgres table. Yeah. On the performance side, you should expect the performance on these Iceberg tables to be comparable to DuckDB on Parquet files, and that's super fast. On ClickBench, you can see that these analytics queries can be up to 1,000 times faster than running the same query directly on Postgres tables. Yeah, there actually has been many attempts to bring OLAP to Postgres. There are so those earlier efforts tries to use their own proprietary format, their proprietary storage and execution engine, but they are usually much slower than purpose-built analytics engines like DuckDB. So as can be shown from the ClickBench. So in the past year, there are several projects have tried to embed DuckDB into Postgres. So PG.DB, so this is one that we actually build on top. So yes, PG Mooncake is actually a sub-extension of PG.DB. We use that for execution. So PG.DB is the official Postgres extension to use DuckDB inside Postgres. This is built as a collaboration of the Hydra team, a YC startup, and a MotherDuck team. So, but they are only focused on execution, and they don't handle the storage. What PG Mooncake adds to it is it handles the storage. So we also have this PG Lake that's from Crunchy Data that was recently acquired by Snowflake. Their offering is similar to our V0.1. It only handles batch workloads. So it's mainly suited for casual data warehousing in Postgres. But their offering is more mature, like more production ready in terms of analytics. So our PG Mooncake, on the other hand, we build on top of PG.DB, and we add a storage layer on top. And we also integrate Moonlink. So as a whole, we actually provide a full HTAP experience that the user actually wants inside the Postgres. Now let's first look at why we want to embed DuckDB, why so many people want to embed DuckDB inside Postgres. So what is DuckDB? So DuckDB is like a SQLite, but for analytics. It's designed to be embedded directly into a host process. It's incredibly fast for analytics, ranking at the tops in benchmarks like ClickBench. And even better, its SQL syntax is very close to Postgres, which means there are fewer incompatibility issues to worry about. And both the Postgres and the DuckDB are highly extensible, which makes this approach possible without actually modifying their source code. So in Postgres, extension can register a new table type using table access method, hook into the planner and executor to change the query behavior, or override the DDL through utility command hooks. And in DuckDB, you can also do something similar. You can write a storage extension to register a new catalog, and you can customize the table planning and execution logic. And this is just a brief overview. There are way more things you can do, way more extension points in both systems. They are very versatile. So as I mentioned, the PG Mooncake is built on top of PG.DB. We use PG.DB to as an execution to use DuckDB to run Postgres queries. So let's first describe how PG.DB works. So at its core, so PG.DB federates Postgres queries to DuckDB. It hooks into the Postgres planner, and when it sees a Postgres query, it rewrites this query into DuckDB syntax. And then as the executor runs this inside DuckDB, and then streams the result back into Postgres, and then convert this result back to Postgres types and return to the user. So it's at its core, it's just a query federation. So PG.DB also allows joining with regular Postgres tables. So this is done by rewriting the Postgres tables of schema tables into a DuckDB table under a special customized catalog called PG.DB catalog. So this PG.DB catalog is registered by a DuckDB storage extension by PG.DB. So this catalog, what this catalog does is it federates the scanning of this Postgres table back into Postgres and uses Postgres to scan this table. And the PG.DB supports scanning this Postgres table in parallel, and they can also push down the filters into this table scan and use this Postgres index to do the scan. However, DuckDB adds this very cool execution of DuckDB execution into Postgres, but the thing that's missing is that there's no storage. If you just use DuckDB to query the Postgres, it doesn't make things much faster. And when compared to just running the same query directly in Postgres on the same table. DuckDB really shines when the data is already in columnar format, if you can directly query the Parquet files, for example. So currently, the PG.DB federates the entire query entire Postgres into DuckDB. So you cannot do some kind of partial query pushdown. So there are many feature gaps and a semantic difference between Postgres and DuckDB. So not every Postgres query can be run in DuckDB. It will be much better to push down only part of the query to DuckDB, to only push down the part they can handle and executing the rest in Postgres. There's already a community PR to add support for insert select for PG.DB. And this PG Lake extension I mentioned earlier from country data has better support for this partial pushdown. So now let's talk about the PG Mooncake. So PG Mooncake solves the problem of data are not already in the columnar format. So what it does is it adds a table access method for Mooncake table. So when you call this call Mooncake create table, it creates a mirror, a real-time Iceberg mirror of your Postgres table, and it's named by C. You can also do it with either local table or remote table. And PG Mooncake achieves this by using Moonlink. PG Mooncake either runs this Moonlink as a Postgres background worker, or it runs like as a standalone service. You can even like have different Postgres all connecting to a shared Moonlink instance. And this Moonlink will subscribe to the Postgres logical operation of those source tables and handle the actual mirroring and keeping the Iceberg table in sync in real time. So PG Mooncake uses Moonlink for the write path. So for the read, on the read path, PG Mooncake instructs pg.db to rewrite the Mooncake tables into a table inside the Mooncake catalog. This Mooncake catalog is registered by our Mooncake's DuckDB extension. It's actually a standalone DuckDB extension. So when a table scan is performed, it just talks to the Moonlink and asks for the count snapshot using an RPC call. And this table metadata will include the count data files, the count delete files, and all those buffers like the arrow and the position deletes. And then we are going to use DuckDB's Parquet scan we modify that to handle all of them and creating the latest view, presenting that to the user. So we want to give users a true HTAP experience. So we need more than just eventual consistency. Specifically, what we want to do is that we want to aim for a sort of session level consistency. That means that if you open a Postgres connection and you write to a table, and now if you do immediately select from the column store table, we want the user to immediately see the changes instead of eventual consistency. So PG Mooncake achieves this by passing the last commit LSN to Moonlink. And Moonlink will wait and only return the Mooncake snapshots that after the request LSN has been applied. And because Moonlink is super fast, even after a large write, a select can be fulfilled in sub-second latency, just like you would expect for a regular Postgres table. So it's important to know that because the limitation of Postgres logical replication, it can't capture all the uncommitted changes, so full HTAP analytics on uncommitted data is not possible. But as discussed earlier, that use case is not our goal. It's very niche. So because Mooncake tables is treated as a logical table rather than individual Parquet files, we can track metadata and statistics at both table level and for each data file and log groups. This allows us to skip irrelevant data during the query, do file skipping more effectively, even outperforming DuckDB on Parquet. So this was tested back in January with the older version of DuckDB. And for PG Mooncake, we've adopted a very modular design principle. So previously, PG Mooncake had to actually hard fork the pg.db, which made the maintenance very difficult. In the latest version, it's now a sub-extension of pg.db. We need no code changes to pg.db at all. And scanning the Mooncake tables in DuckDB is also packaged by itself in a separate DuckDB extension. And this extension can be either used by itself in a standalone DuckDB to query Moonlink from DuckDB, or you can use it from Postgres in the context of Postgres and PG Mooncake. So it's very modular. And the same modular design principle applies to Mooncake, enabling a composable HTAP framework. So while this talk, I'm mostly talking about like Postgres, Iceberg, the Mooncake design also supports other OLTP system and lakehouse format, such as MySQL and Delta. In fact, we already added support for ingestions from Kafka and event streams like OTel, and the execution engine is also not limited to DuckDB. We actually already supported Apache Data Fusion, and we can even leverage Spark as well in the future. So I think this is a very exciting time to rethink OLTP and how it can integrate with the lakehouse. So the lake base is still in its early days, and there are many open problems to explore. And Mooncake provides a way for the ETL, but can we also do the reverse ETL? Like, can we create a Postgres tables from an Iceberg table or Delta table more efficiently? That will also be an interesting thing when we try to bridge this lake base and the lakehouse. And on the lakehouse side, we can do data sharing. We can share data on the lakehouse cross organization. But can we also do the same thing as the Postgres side? Can we share the Postgres tables across different organizations? The analytics worlds are moving towards open formats, but can we also derive an open format for OLTP? With the open OLTP format, we might be able to run some of the Postgres-related workloads outside of Postgres itself. For example, we can run some of the ETL. We can directly convert into the open OLTP format, run everything outside of the Postgres using Spark, for example. It will be much, much faster. Also, on the Postgres side, we have index built on Postgres, but can we also build secondary index on Lakehouse to serve lookups and search workload? So we don't need to prepare the Go data in Lakehouse and load it into another engine to serve it. Now we can directly serve from the lake. Can we do that? And also with OLTP and OLAP bridge through the composable HTAP layer, now can we implement some kind of smart query routing to route between these two engines? And finally, can we leverage something like unit catalog to build a universal data governance that across both transactional and analytical data? Yeah, thank you for attending my talk. If you have any questions about Mooncake after this talk, feel free to ask in our Dev Slack channel. I'm also encouraging you to considering joining Databricks and the Lake-based team. Let's build a future data system together. Yeah, thanks.
All right, I will clap on behalf of the audience. Cheng, thanks so much for doing this. We have time for a few questions. If you want to unmute yourself, fire away, go for it. So if you go back to the previous slide, when you had the sort of lake base and lake house, so
Yeah.
should I understand that Mooncake with the Moonlink piece, that's that's in between the two of them, right? Like you're positioning this thing as like this. I mean, I understand that it can run as a worker directly inside Postgres, but if you're saying I want to start connecting with Kafka, I want to start connecting with OpenTelemetry stuff, like and then actually I guess the lakehouse doesn't matter either. Like whatever the query engine is, like in that environment, it has to be its own sort of middle service. Like it can't be like is that your vision how you want to position this thing?
Yes. Yeah, we definitely focus. Yeah, we've definitely not just focused on the Postgres side, and we actually have like a more focus on the Lakehouse side. But I think, yeah, as one thing you said, it can be a middleware. But on the other hand, I think, as I mentioned earlier, I think for things like this ingestion, it's not really the hard part is not really just about the ingesting, like the middle part. I think
Yeah.
it's sometimes the destination is not real time enough. You want to build a layer on top to make that thing more real time. So it will be more something like something wrapped on top of Lakehouse. It's kind of a managed Lakehouse, or something built on top. So in fact, so while we are already building this ETL, so before we are getting acquired by Databricks, we are actually also discussing internally, try to build some kind of indexing layer on top of the Lakehouse and try to directly serving from the Lakehouse. So in that sense, it's more like a managed real-time Lakehouse on top of the already existing ones.
Got it. Okay. And then when you had this sort of comparative analysis of the existing tools that are out there, and there's Citus, Microsoft bought those guys, that was shared nothing. So that doesn't exactly map what they were, which what you guys are trying to do. Swarm 64, they were FPGA accelerator, but then they got
Mhm.
acquired by ServiceNow. And then
Yeah.
now it's in RaptorDB, or whatever the ServiceNow's thing. I think that's all software based. But again, I think in those systems, and the other one, Vitesse, like with those guys, they're intercepting the queries sort of similar to timescale and running off to like separate column store. Um, I mean, in some ways, like you're not. All those other systems have to build their own OLAP engine, but now since you guys are coming along 5, 6, 7, 8 years later, that you can take advantage of all the people that have built things like DuckDB or Data Fusion, and it's really about the like just relying on that sort of commodity hardware or commodity components to do the query execution. The magic, the hard part is really sort of like reconciling the change log and maintaining, materializing results that you can then feed up to or feed into Data Fusion or into Postgres as needed. That's how I should understand what Mooncake is trying to do, right?
Yes, yes, we definitely don't want to build. There are some. We don't want to reinvent the wheels. So we want to use existing execution engines like DB Data Fusion. They're already very good. They're also very good distributed execution engine that we can federate to.
Got it.
Yeah.
Okay,
So that's
awesome.
for the analytics part. For the HTAP part, we are also trying to solve a much simpler problem compared to the monolithic HTAP that we are trying to solve back at single store. We are
Yep.
mostly just trying to replicate what the already does in Postgres. So that's a much easier problem compared back then. Yeah.
Got it. Okay. Jignesh, you have a question?
Yeah, nice talk. I wanted to go back to the earlier part of where you started with the motivation, and you talked about how HTAP applications are, you have to look really carefully at what the HTAP applications do. Uh, and as a backdrop, the database community, if you look at the traditional transactional vendors like SAP and Oracle, they added hybrid stores with row store and column stores in their products a long time ago, ran into same types of problems where some of the workloads tend to be problematic. So if you go back to that, what are the drivers that you're seeing from the application perspective that need this type of HTAP, that need that speed? Are these applications that want to, for example, query the analytics side and are feeding into some AI pipeline? Because for those, it's okay if you don't get quite the right data. The fraud example, I wasn't quite sure it resonated. So I was just wondering if you could talk a little bit about the types of applications that are driving the need for the types of things that you described in Mooncake.
Yeah. I think the main workload we are looking at Mooncake was fast analytics on fresh data. What that means that we want to decrease the latency between where your data is generated to where you can run queries on top and then make decisions based on that. I don't have like a concrete example use case of that, but it's more of that.
For fraud, there was like in the old days, this
Yeah,
is what Splice Machine was still a thing. They were running from Visa. So as you're doing the swipe on your credit card, they wanted to run fraud detection like at the point of sale.
yeah, but for fraud, you actually need analytics in transactions. That's a much harder problem.